In this video, I would like to talk about differentials of functions with more than one input variable. Let's first revise what's the differential in the case of a single variable calculus. The differential associated to the function f of x can be written as df equals df over dx times dx, or if you want, f prime of x times dx. This is pretty self-explanatory, and this is equal to the derivative of f with respect to x, which can also be written in this form. This is just intuition. df means f of x plus dx minus f of x, if you want. This can also be written as f prime of x times x plus dx minus x, because this is also equal to dx. Or, if you want, f of x plus dx equal to f of x plus f prime of x times x plus dx minus x. What this equality tells us is that if we consider a function, and here's the point x, this is f of x, and here's the point, let's say, x plus dx, which is very small. I'm exaggerating a bit, it's a bit too far, but this should be very close to x. And what this formula is telling us is that the function at f of x can be approximated by the tangent line at the point x to the function. Okay, so this is the point f of x plus dx. The slope of this line is given by the derivative of the function at the point x, f prime of x. This drawing is not so clear maybe, but this is what this equation is telling us. And it is very simple in terms of single variable calculus, but this reasoning can be extended to multivariable calculus, and in particular, instead of approximating the function at the point x with a line, as an approximation we are going to use a plane in 3 dimensions. As you can see, this expression here represents a line, but where does this come from? This comes from the Taylor series expansion. If you take a look closely at this relation, if we, for instance, call the point x plus dx as x, let's substitute x in place of x plus dx, and in place of this x we will substitute x0. So if we do this, we have f of x is equal to f of x0 plus f prime of x0 times, this is x, and instead of this I will write x0, so x minus x0. This expression is the Taylor series expansion of the function f at the point x0, so we are approximating our function near the point x0. That's what this is telling us. If the 2 points are very close to each other, infinitesimally close, we can write an equal sign. In general, this equal sign should be replaced by an approximation sign if we are considering a finite distance between x0 and x. And this is a line because this is a constant, and f of x is our function y. Y is equal to f of x in general. So y is related linearly to the independent variable x in this relation. So this must be a line with this slope f prime of x0. In general, if we want to extend this reasoning to multivariable calculus, let's consider just 2 variables for simplicity, but the thing is very similar for a larger number of input variables. So if we have a function f of xy in this case, and we want to approximate the function near the point f of x0, y0, we can write it near that point as a linear combination of the variable x minus x0 and the variable y minus y0. So we can write, for instance, a plus b times x minus x0 plus c times y minus y0. And this equality holds only when the point that we are evaluating our function at is very close, infinitesimally close to the point x0, y0. We need to find the coefficients a, b, and c in this case, but this is not so difficult. For instance, the value of a can be computed from f of x0, y0, because if we insert in this relation x0, y0, we get b times x0 minus x0, which is 0, plus c times y0 minus y0, which is 0. So we are left with a. So a must be equal to this thing right here. B instead is equal to, we can take the derivative of this expression with respect to x, because this is a constant with respect to x, so that's 0. The derivative of this part gives me b times the derivative of x minus x0 over x, which is just 1, so we get b. plus c times the derivative of y minus y0 with respect to x, but that's 0 because y and x are independent variables, so b is equal to the derivative of f with respect to x. And remember that the function is computed at the point x0, y0. So this derivative must be evaluated in general at the point x0, y0 because this equal sign holds only when x and y are very close to the point x0, y0, but these are constants, so this derivative cannot depend on x and y. It must depend on x0 and y0 because x0 and y0 are the constant parameters here, while x and y are independent variables, so they are variables, they are varying. Similarly, c is equal to df over dy, evaluated at the point x0, y0. So, all in all, we can write down f of x, y equal to f of x0, y0 plus df over dx computed at the point x0, y0 times x minus x0 plus df over dy at x0, y0 times y minus y0. Remember, I will stress this out ad infinitum. This equal sign holds only if x and y are very close to x0, y0, infinitesimally close. So if we take this term to the other side, we have f of x y minus f of x0 y0. But what is this? This is the definition of a differential because we are evaluating the function at two infinitesimally close points and then subtract those two evaluations. And this is the differential. This is equal to df over dx at x0, y0 times x minus x0. But remember, those 2 points are infinitesimally close to each other. So this is just equal to dx plus df over dy x0, y0 times dy similarly. So y and y0 are very close to each other. We can just insert an infinitesimally small quantity dy here. And this is our important relation. Df equals df over dx at x0, y0 times dx plus df over dy at x0, y0 times dy. And this is what we also used in the last lecture to evaluate one derivative, and in particular the function f in general can depend on x and y, but x and y can also depend on other variables, for instance the variable t. This is something similar to what happened in the last example, in the last lecture. In this case, so let's rewrite what we just obtained here. Df equals df over dx times dx. I will not write the dependence of f with respect to x0, y0 plus df over dy times dy. If we divide by dt, this expression we get df over dt equal to df over dx times dx over dt plus df over dy times dy over dt. This is something that we used in the last lecture to evaluate the derivative of a function of the form f of x plus ex times t, comma y plus ey dot t. And we had to take the derivative with respect to t and then set t equals 0, if you remember. In this case, if you apply this formula, we have to do the following computation: df over dx. In particular, take a look at the first argument. It's x plus ex times t, so we should write down x plus ex times t, and then take the derivative of this argument here with respect to t, just like this thing is telling us. And the derivative of that is just ex plus df over dy plus ey times t, so that's the second argument, and then take the derivative of the second argument with respect to t, so that's ey. As the last step, then we had to set t equals 0, so that was something that had to be done in addition to this step here, but this is essentially what I wanted to convey in this lecture.